The next paper is on the selectivity of crotonaldehyde hydrogenation over platinum, authored by M.A. Vannice of Penn State and B. Ban of University of Colorado. And the paper will be presented by Professor Vannice.
Thank you. In regard to catalyst design, what I'd like to do this afternoon is try to give you an idea of some of the thinking processes we've been going through based on some of the experimental work we've been involved in for perhaps the last 6 or 8 years. We initially were quite heavily involved in studies pertaining to hydrogenation of carbon monoxide, particularly the effect of titanium upon reaction rates occurring on group 8 metals dispersed on titanium. We found in that case that particularly with certain metals, the more noble group 8 metals, very marked rates of enhancement were observed when titanium was used as support and was properly pretreated. I'll show you that in just a moment. Well, we got to thinking, as a consequence of those studies, is this phenomenon that activates the CO molecule restricted to that molecule, or could we perhaps utilize that to see if we could activate carbonyl bonds in general? The next probe reaction that we used to test that hypothesis was to hydrogenate acetone to isopropyl alcohol. In a very similar fashion, and I'll show you that again in a moment, we found that again with titanium, it could invoke very great rate enhancements, well over 2 orders of magnitude. Well, we were encouraged by this, and we proposed a model that I'll review very briefly to account for this. We decided to push our system and our thinking one step further and say, could we indeed design a catalyst that might give us the capability of going into a more complicated molecule, for example, one with both carbon-carbon double bonds and a carbonyl bond, or a phenyl group and a carbonyl bond. Could we go in, use this approach, and selectively activate the carbonyl bond toward hydrogen and leave the rest of the carbon unsaturated bonds intact? And that's the aspect I'm going to be focusing on this afternoon, is that last topic. Now, just as a very brief reminder, in this case, with regard to the past results and some of the characteristics we've observed, and more or less to bring you up to our point of thinking on this, these represent a very brief summary of the results for both carbon monoxide hydrogenation and acetone hydrogenation. As I mentioned, titania has been able to produce the greatest rate enhancement on these on these reaction rates. We see differences, however, dependent upon the support we use. For comparison, if we look at platinum powder and platinum on silica, which is known to be a relatively inert support, we see very similar turnover frequencies under a standard set of conditions of 1 atmosphere and 275 degrees centigrade. If we put the platinum on alumina, for example, the activity goes up close to an order of magnitude. The same thing is seen with silica alumina. But finally, if we use titania, whether we treat it at low temperature at 200 degrees centigrade or a high temperature reduction of 500 degrees centigrade, we see very marked rate enhancements when these are characterized by turnover frequencies. If we characterize the turnover frequency by the reduced amount of chemisorption that occurs in these titania systems, primarily due to an overlayer coverage of TiO2, as was mentioned briefly before, we get very large rate enhancements. If we take a more conservative estimate based upon the crystallized size that existed in the low temperature reduced catalyst, which has very normal chemisorption properties, we still see 2 orders of magnitude rate enhancement. The interesting thing to note here is that this is not due to a decrease in the activation energy. For the more active titania catalyst, the activation energy is actually somewhat higher, very reproducibly higher. If we now go to acetone and compare, we see a very similar sequence of rates occurring. We see that platinum powder and platinum on silica are again quite similar. If we look at alumina, it's about the same. In this particular case, platinum on titania after a low temperature reduction is not much different. But if we take the platinum on titania, reduce it at 500 degrees, we see a very, very significant rate enhancement. This is an average value, but it's well over 2 orders of magnitude more active for the hydrogenation of acetone to isopropyl alcohol. Again, if you look at the activation energies, this higher rate is not due to a lower activation energy. You see it's essentially the same as the others, particularly that of the platinum powder and platinum silicate. Well, these were the results that led us up to this test, and about 5 years ago we had proposed a very simple model to account for the higher rates of hydrogenation of the CO molecule, just by invoking that if we put platinum and titanium, TiO2, when it's reduced at higher temperatures, it can become non-stoichiometric. It can also migrate over the platinum surface. We think that this higher activity is predominantly due to the increase in the interfacial region here, and that we have non-stoichiometric characteristics, for instance, Ti3+ cations that are created, perhaps oxygen defects, we're not certain. But these, for instance, the Ti3+ cations might polarize or interact with the oxygen in the CO molecule to enhance that bond hydrogenation. So this is the general model that we were utilizing in these other test reactions. That same sort of model was capable of explaining the activity for acetone hydrogenation. If we look at our next test reaction, it's crotonaldehyde hydrogenation. It's a 4-carbon atom. We have a conjugated double bond system. We have the carbon-carbon double bond here, a carbonyl bond at the end. This is also a more complicated system. We have a network of reactions. If we look just at the thermodynamics involved, of the two intermediate compounds that are formed, butyraldehyde or crotyl alcohol, we see that the free energy certainly favors the formation of the butyraldehyde. And the free energy change is about double that of the crotyl alcohol. Of course, complete hydrogenation of both the bonds gives you butanol. Now, our typical reaction conditions are cited here. These are slightly above room temperature, 1 atmosphere pressure, quite high ratios of hydrogen to the reactant. I might also mention here that with regard to our results, and as indicated by the thermodynamics, platinum catalysts are not the best catalysts for that reaction. The literature teaches very quickly that these catalysts are very good for the formation of butyraldehyde, and in essence, the platinum catalysts in the literature give you 100% selectivity to butyraldehyde. We observe the very same thing with our typical catalyst. If we look at the reaction rates involved for this, we're now looking at the disappearance of crotonaldehyde over platinum. These are all under differential reaction conditions, typically between 1 and 10%. If we now look at the turnover frequencies for this reaction, we see that they're very, very similar for platinum and silica, for platinum and alumina, for platinum and low temperature reduced titania, for platinum powder, and for a physical mixture where we take the platinum powder and physically mixed it with the titania and then reduced it. We see in this case we get essentially the same turnover frequency, values very close to the singular value. If, however, we put the platinum in titania, we give it a high temperature reduction, we find that the turnover frequency per site is much, much greater than it is on these other catalysts. Again, note, very interestingly, and similar to the previous results, that the catalyst in titania, the catalyst utilizing titania, do not have a lower activation energy. In fact, again, these activation energies are somewhat higher. I want to stress at this point that these low values do not imply diffusion limitations. We tested for those, and in addition, if you go to the literature and you look at activation energies for the hydrogenation of olefins, these values range in the order of 4 to 6 kilocalories per mole. So they're well within the values expected for hydrogenation of carbon-carbon double bonds. Our emphasis here was on selectivity, and we wanted to answer the question, could we affect any differences in the activation of that carbonyl bond to give us crotyl alcohol? If we examine this, we find that only the titanium-supported catalyst gave us any selectivity to crotyl alcohol. Now, as I mentioned, platinum and silica, platinum and alumina gave us results identical to those in the literature. We saw only butyraldehyde form. At very high conversions, which we did in some cases, we started to see some butanol form. However, this is the titanium on the low temperature reduced sample. Here for the first time we saw some capability for forming the crotyl alcohol. We had 4 different crystallized sizes of platinum present as determined by chemabsorption measurements. They're not markedly different. They range from about 10 to 25 angstroms average particle size. But we see with this particular system, we have been able to achieve a maximum of about 13 mole percent crotyl alcohol in our selectivity. So even with this system, we've been able to go from non-detectable amounts of crotyl alcohol, in other words, turnover frequencies we could not detect, to very significant rates of production of crotyl alcohol. You notice that the rate of reaction was higher per site on the high temperature reduced sample. If we now look at the effect of the pretreatment on the platinum titania catalyst, what we find is that the high temperature treatment further enhances the capability of these catalysts to activate the carbonyl bond. We have not tried to optimize these systems, but the best catalysts we've observed to date are those, is this catalyst in particular. With this particular sample, we've been able to get 37% crotyl alcohol. The only other product that we've observed is butyraldehyde. As you can see in these other samples, the high temperature reduced samples tend to have somewhat higher selectivities to crotyl alcohol. Again, 37% is the highest. We see in some cases also the formation of butanol, complete hydrogenation, and that appears to be almost certainly the complete hydrogenation of the crotyl alcohol form to go on to butanol. So it's very complicated. We want to stop with somewhat of an intermediate product, and of course we can do so with varying degrees of success. What is the model? Again, we've stuck to our relatively simple model. We'll probably try to keep testing it until we destroy it, and then we'll have to start over and change our thinking. But at the present time, it seems to be working relatively well, and we use the same sort of ideas in the sense that on a typical platinum catalyst, say platinum and silica, we suspect we have absorption on the carbon-carbon double bond. That's how an olefin would prefer to absorb in platinum, and all we're doing is hydrogenating this selectively to give us the butyraldehyde. If we go with platinum and TiO2 at low temperature reduction, we probably have only a very limited number of these non-stoichiometric sites exist, or these defect sites in the non-stoichiometric titania. They probably only exist at certain locations at the interface at these low temperature reductions. Here we think that we have some sort of an interaction, perhaps some polarization of the bond here that facilitates this hydrogenation step. After the high temperature reduction, as was pointed out, one major aspect of the titania catalyst systems is the migration of this TiOX species across the metal surface. So we enhance the interfacial region, the interfacial surface region between the metal and the titanium oxide. We suspect in these cases, we know that we have Ti3+ and perhaps even Ti2+ cations. We are proposing that these are probably the ones interacting with the carbonyl bond to enhance its selectivity to crotyl alcohol. Concomitant with this, and something we don't admittedly understand completely, we suspect we are also somehow decreasing the chemabsorption capacity at the carbon-carbon double bond, because in some cases we do not see any butyraldehyde formation at all on our best catalyst. So we think that there's some sort of a perhaps inhibition of the absorption here, but there is, whatever occurs still allows the interaction here. So this is a fairly simple model. We're still utilizing it, and we plan some further tests in the future with other types of more complicated molecules. Well, in summary then, I'd just like to say that typical platinum catalysts give us only butyraldehyde. However, if we put the platinum on titanium with varying pretreatments, we have varying degrees of success in being able to change the selectivity to give us a crotyl alcohol. We see a 10-fold higher turnover frequency on this high temperature reduced platinum sample, even though the activity per gram of platinum is similar. I mentioned the selectivity. To date, we've gotten up to 37%. If you go to the literature, you probably want to use osmium or ruthenium for higher values to begin with. But our idea here was to see if we can increase the active sites that are responsible, the active sites associated with platinum, that are responsible for the selective hydrogenation of these carbonyl bonds. And at this point, our model is still, we still favor the model where this is all occurring at the interface, and it's a function, therefore, of the efficiency of gaining this interfacial region when you have a support that can migrate across the surface. I'd like to acknowledge this was the sponsorship of DOE and my co-author, Dr. Sen. Thank you very much.
We have time for one question. Okay, go ahead.
The question I had was, is the selectivity change reversible? Can you oxidize the catalyst and get the selectivity back of the LTR catalyst?
We've never tried that as far as the redox techniques to go ahead and recrystallize the TiO2 and then redistribute it. I suspect we would get some of that back. But as you can see, there's some variation that we at this time attribute to the fact that we cannot control how this is spread across the platinum surface.
As a matter of fact, the CO hydrogenation involves cleavage of the bond, whereas all of these involve no cleavage. So in that sense, the analogy is not quite complete, isn't it?
Well, it depends. There's also the CO molecule is also. It's a good point. The CO molecule is also bonding in a. You have a singular bond there on the metal surface, and with these other molecules like acetone and the crotonaldehyde, it's still not clear to us how exactly this is sitting down on the platinum surface. And I suspect what's also happening is we're weakening that platinum carbon interaction for the larger molecules. Yeah, it's more complicated than just that aspect.
Okay. Thank you very much.